Hello, everyone. Welcome to the Graduate Online's Combinatorial Colloquium. Today, we have Venkatesh talking about the polynomial method beyond simple evaluations and roots. But before I turn it over to him, I would like to remind everyone about our community statement. The first thing is we are all learning. The second part is everyone has something to contribute. And finally, no one has all the answers. And so just things to keep in mind during the talk. If you have any questions, feel free to ask them to the speaker directly, or you can type them in chat and one of the organizers will find an appropriate moment to slip it in. But without further ado, Venkatesh, you have the floor.
Thank you. Thank you. It's good to be back. This has been a good colloquium for me since the last 2 years. I've been fortunate to give 2 talks based on some of my graduate work, and today, yeah, it's good to be back and essentially speak on things that are a continuation of things that I had worked on earlier. So yeah, so today I'll speak about the polynomial method, or rather I should say I'll speak more about the polynomial method because there has already been one talk introducing the polynomial method to this audience. So yeah, the title is Beyond Simple Evaluations and Roots. And that's quite intentional because the beginning of this talk is probably from where the previous talk ended. So yeah, so let me just quickly recap the combinatorial Nullstellensatz of Alon. So I'm writing it slightly differently, and I'll sort of get into why I have written it this way. So let F be an arbitrary field and S1 to Sn be finite subsets. Then I claim that the set of monomials of the form x1 raised to alpha 1 to xn raised to alpha n, which I denote succinctly by this notation script x raised to alpha. The set of monomials of this form where the vector alpha ranges in the set 0 to size of S1 minus 1 cross 0 to size of Sn minus 1. Essentially, every alpha I is at most size of Si minus 1. The set of monomials indexed by alphas of this kind, this is a basis of the function space f to the S1 cross S2 to Sn. So every function from the product set S1 cross S2 cross Sn to f can be represented uniquely as a linear combination of monomials from this set. Right. And this is precisely Alon's combinatorial Nullstellensatz. It's just a contrapositive form. So the other form says, if there is a formal polynomial, that's a linear combination of monomials where each degree, the degree of each xi is strictly less than size of Si. It is if it's a linear combination of monomials where each alpha I is at most size of Si minus 1, and if this is a non-zero polynomial, then there is at least one point in the grid S1 cross Sn where the polynomial takes a non-zero value. Right. So this is simply a contrapositive of the statement which Alon writes in his paper. But I wish to write the statement this way because it's at least it gives a more linear algebraic intuition as to what the statement says, and extensions of this statement are easier to write in this form. All right. So just to quickly once again recap what this says. In 2 variables, let's say S1 cross S2 is a product set in F cross F, where F is some field. And what the Nullstellensatz says is, it really doesn't matter what S1 and S2 are. Simply take the finite sets 0 to mod S1 minus 1 in the x-axis and 0 to mod S2 minus 1 in the y-axis over the non-negative integers. And this finite set, this finite product set of non-negative integral tuples, 2 tuples, index the set of all monomials which will form a basis of the whole function space on S1 cross S2. Right. So this is precisely Alon's Nullstellensatz, and we'll sort of start from this point. So in other words, if we are to express every vector, so instead of thinking of these as functions from the product set into F, if you think of this as a vector space with dimension size of S1 cross size of Sn, and if you think of these as evaluation vectors, then if we are to express every vector in this vector space as an evaluation of a polynomial, then the monomials in this set x to the alpha, where alpha ranges in this grid, these monomials are enough to give me a basis of this vector space. Right? Now it's quite obvious that any vector space, you can always write down the vectors as evaluations of some polynomial by Lagrange interpolation or whatever interpolation method you would like. The relevant question here is, what is the smallest set of polynomials that you would require? And since we are dealing with vector spaces, it's a linear algebraic question. What's a nice basis? And the Nullstellensatz simply says, well, you have a nice basis of monomials which can be combinatorially described in this way. Right. Right. So we are interested in extensions to multiplicities. And by multiplicities, what I mean is we will now look at not just evaluations of polynomials, but also evaluations of the derivatives of polynomials. Right. So the usual derivative in the sense of calculus doesn't really apply when you consider polynomials over finite fields. And there's a simple adjustment to this. So let's say we have two sets of coordinates, for instance, x1 to xn and y1 to yn. I'm simply taking a polynomial p of x here and considering a Taylor-like expansion of this polynomial about the arbitrary point x in the indeterminates y. So you could plug in x to be some fixed point A, look at its Taylor expansion around the point A. Instead of looking at classical derivatives, just look at it as a polynomial in the indeterminates y. There will be some coefficients. These coefficients are defined to be the Hasse derivatives of the appropriate order at that point. But now you can take the point to be an arbitrary point and replace the coordinates with indeterminates. And you might as well get these coefficients as polynomials in the variables x1 to xn. Right? And these are defined to be the corresponding ordered Hasse derivatives of the polynomial. The only difference between the Hasse derivative and the classical derivative is a factorial as a constant, 1 by factorial as a constant. And that is precisely how you avoid this issue of the factorial being 0 over a finite field and then the corresponding coefficient not being defined. So you don't bring in factorials at all. Right? So in this sense, derivatives can be defined over finite fields as well for polynomials. More generally, if you need a derivative of a function, you need to fix a polynomial representation and then you can talk about its derivatives. Right? So for the multi-index alpha, the alpha order Hasse derivative of the polynomial p is defined to be the alpha coefficient in this expansion. All right. So how do we extend the combinatorial Nullstellensatz or the Nullstellensatz type of statements and arguments to encapsulate derivatives? So let me just go back and revisit the statement. In order to express the vector space f to the S1 cross Sn as a set of evaluation vectors where each evaluation vector is comes from an evaluation of a polynomial, the monomials x to the alpha, where alpha ranges over the suitable grid, is enough. That gives you a nice basis of this function space. All right. Okay. So now let's go into multiplicities. So we need to fix a parameter for the multiplicities. We are taking derivatives. So the question is derivatives up to what order? And the order is going to be m. So when you fix the multiplicity parameter m, the set script m sub m denotes the set of all multi-indices. I'm really sorry. Yeah. Script m sub m denotes the set of all multi-indices alpha such that the total degree of alpha is at most m minus 1. And m sub m is supposed to denote the set of all derivatives that you take. So when you fix the multiplicity parameter m, you take derivatives of order at most m minus 1. When you fix the multiplicity parameter 1, you take all derivatives of order at most 0, which is just the simple evaluation. Okay. Fine. So how many multi-indices do you have for multiplicity parameter M? Well, that's precisely n plus m minus 1. Choose n. It's a simple counting argument. Okay. So now what's the question? What's the extension? The question is, if we are now to express an even larger vector space, where the coordinates of every vector are not indexed by just the points of the grid, but by points of the grid as well as the multiplicities, the multi-indices of derivatives. And what sort of expression are we looking at? Well, now every vector is some derivative of a polynomial at some point. Right? So a vector here should be representable as, take a polynomial, and for every component you have a corresponding point in the grid and a multi-index, and the evaluation should be the derivative corresponding to that multi-index of the polynomial at that point. Right? And if you are to express this vector space in this way, this can always be done. Just as you had Lagrange interpolation in the simple case, you have Hermite interpolation in the multiplicity case. So there is always a polynomial which will give you such an expression for any vector in this vector space. Now the question is, what's a nice basis, or how small a basis can you, how small an expression can you have? Right? So what is an F basis? More importantly, is there a nice combinatorial description to such an F basis? And the answer is yes. So let me just introduce a few more notations. So G will represent this standard grid of non-negative integral vectors. The grid in the vector space is fixed to be S1 cross S2 cross Sn. And the corresponding integer vectors are given by 0 to size S1 minus 1 cross up to 0 to size Sn minus 1. And this integer grid is represented by G. I'll fix this notation. For any multiplicity parameter M, let me just define G sum script M sub M. So I'm borrowing this notation from the idea of Kronecker products of matrices. Right? And let me just, so this is what the expression is. This product is supposed to be the set of all vectors of the form gamma 1 times size of S1 plus alpha 1 dot 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 gamma n times size of Sn plus alpha n, where alpha varies over the grid G and gamma varies over all multi-indices of the derivatives that you would want to take. What exactly is this? It's very easy to understand by a simple example. So for simplicity, let me say the grid has just 4 points in 2 coordinates. Okay, it's a square. And I'm taking the multiplicity parameter to be 3, which means I'm considering all integer vectors with total degree of most 2. And the set G sum M3 is essentially this. This should remind you of a Kronecker product of matrices, because what I'm really doing here is place a copy of G at every point, at every multi-index in M3. And the expanded set of monomials that I get, that is G sum M3. Okay. Now these are integral vectors. These will index a set of monomials, right? Very naturally. This gives you the multiplicity extension of the combinatorial Nullstellensatz. Okay. So you will find this in 2 independent works, one by Koparty from 2015, and then by Gale and Martinez-Peña in 2017. Gale and Martinez-Peña considered this in an even more general setting. So for any multiplicity parameter M, if we are to express this much larger vector space, where every vector is an evaluation of not just a polynomial, but polynomial and its derivatives up to order M at the points in the grid, then the set of monomials coming from the sum G sum M sub M is an F basis. All right. So going back to this figure, if my grid is here, and if I'm considering a vector space of an appropriate dimension where every evaluation vector, where every vector in the space is an evaluation vector of a polynomial and its derivatives of order at most 2 at all points in the grid, then it has a unique expression as a linear combination of monomials in G sum M3. Right. So that's the multiplicity extension of the combinatorial Nullstellensatz. I think this is a good time to pause and take questions if there are any.
How would the standard formulation of this Nullstellensatz then be? So, because you said you reformulated the Nullstellensatz as this basis theorem.
Right. That's a nice question. Yeah. So the standard form says if you have a non-zero polynomial in the span of these monomials from G sub m sub m, then there is a point and there is a derivative corresponding to which when you take the derivative of the polynomial at that point, the evaluation is non-zero. At least one component in one vector, at least one component in that evaluation vector is non-zero. Right? It cannot be a non-zero vector, that's all. So as a long evaluation vector, if it should be non-zero, all it says is there is a point and there is a derivative corresponding to which the value is non-zero.
Okay, thank you.
Okay. Yeah. All right, so yeah, let's go ahead. Why is this interesting? Why should we care about such extensions? So let's go to a classical problem from combinatorial geometry called the finite-field Kakeya problem. Some of you might be familiar with this, but let me recap the basic definitions. So a set K in FQ to the n is said to be a Kakeya set if for every non-zero vector B, so non-zero vector B is supposed to represent a direction in the vector space FQ to the n. So for every direction B, there is a point A, such that the line along the direction B passing through the point A, I denote it as LAB, which is parameterized as A plus TB, where T varies over SQ. This line is contained in K. Okay. So a Kakeya set in this vector space is any set such that for every direction in the vector space, there is some point such that the line passing through that point with this direction must be in the set. Okay. A trivial example of a Kakeya set is a full vector space. But of course, Kakeya sets can be much smaller, and in fact, constructions of Kakeya sets for smaller size are fairly complicated. So let me not go into a specific construction of a nice Kakeya set. Instead, let me just jump to the problem that we wish to tackle via the polynomial method, which is what is the smallest possible size of a Kakeya set? Right? For instance, can there be Kakeya sets of size q to the n minus 1 in a vector space of size q to the n? Or a Kakeya set of size q to the n by 2? Or something much smaller than q to the n, q square root of q to the n, q to the n by 2. Can there be Kakeya sets of this size? So the definition says for every direction there is a line that is contained in the set. It should be indicative that the size should be fairly large, right? At least intuitively. Such sets cannot be very small. So in 2008, Dweer and Alon and Tao. So I've written it this way. The initial argument was given by Dweer, and Alon and Tao sort of polished the argument a bit further to get better bounds. So Dweer, Alon, and Tao in 2008 showed that any Kakeya set in FQ to the n must have size at least q to the n by n factorial. And the proof of this is via the polynomial method due to a simple observation. What they really show is a set, the Kakeya set has size at least n plus q minus 1 choose n, which is lower bounded by binomial estimates by q to the n by n factorial. So what we are really going to consider in this proof are polynomials in n variables of degree at most q minus 1. Okay. And how does the polynomial method proof go through? So this is a proof via the simple application of combinatorial nullstellensatz. And then I'll sort of elaborate on how the multiplicities help us get a better bound. So what did Dweer and Alon Tao show? So suppose the size is much lesser than this. Okay. Then, well, there is a polynomial in the span. So by Nullstellensatz, every function over FQ to the n is in the span of these monomials. So there is a polynomial which is non-zero such that the degree is at most q minus 1. and which vanishes at every point in the Kakeya set. Why is this true? It's a simple linear algebraic statement. Set up a linear system where you have one constraint for every point, and the monomials are all of degree at most q minus 1. You will get a linear system with number of constraints strictly less than the number of variables. And therefore, it's a homogeneous system, so it must have a non-trivial solution. That solution is a non-zero polynomial. So there will be a non-zero polynomial in this span by the Nullstellensatz, such that the degree is at most q minus 1 and it vanishes at every point of the Kakeya set. Let's split this up into its homogeneous components. So P0 is the homogeneous part with degree 0, PQ minus 1 is the homogeneous part with degree q minus 1. Now fix any direction. And by the Kakeya property, what we know is that there is a point A such that the line LAB is contained in the Kakeya set, and therefore P restricted to this line vanishes. Right? So P of A plus TV is 0 for every T in FQ. But this is a line with Q points, and P is a polynomial with degree at most Q minus 1. So when you restrict it to this line as a univariate polynomial P of A plus TB, where you can think of T as an indeterminate. This univariate polynomial has a degree at most Q minus 1, but it vanishes on Q points in the line. Therefore, it must be the zero polynomial. All right. Now let's look at the coefficient of the highest polynomial, t to the q minus 1. It's a zero polynomial, so the coefficient of t to the q minus 1 should be 0. But if you just compute the expressions, you will get that the coefficient of t to the q minus 1 is in fact the q minus 1th homogeneous part evaluated at the direction vector b. So this implies pq minus 1 at b is 0. And now you can vary over all non-zero b's, and then the claim follows. What I mean here is that you can conclude that p must actually be the zero polynomial, which will contradict the assumption that px is non-zero. And therefore, the size of k must be at least n plus q minus 1 choose n. Binomial estimates will then give q to the n by n factor as the lower bound. So a very simple-minded application. In fact, this is a kind of proof that should remind you of other applications of the Nullstellensatz that you might have seen in the earlier talk. Right. So how do multiplicities come here? So it turns out that the size of Kakeya sets, the minimum size of a Kakeya set is much larger. So Dweer, Kopati, Saraf, and Sudan, 2013, showed that the lower bound is in fact q to the n by 2 to the n, which is significantly larger than q to the n by n factorial. So how do they do that? So that's where multiplicities come in picture. So yeah, there is a setting of parameters here which one might conveniently ignore in order to understand just the gist of the proof. So I'm thinking of L as a free parameter, which is restricted to be some large multiple of q. Otherwise, it's free. It's just ranging across multiples of q and nothing else. And I'll fix the multiplicity parameter m to be 2l minus l by q, and a degree parameter for my polynomials to be l times q minus 1. Nothing great about this. This comes via reverse engineering. So you start with some m and some d, and then finally figure out which values of m and d will make your proof go through. That's what it is. So one might ignore these settings. But here's the thing. If you're considering polynomial evaluations of the derivatives up to order n minus 1 or up to degree n minus 1, and the degree of the polynomial is at most d, then you have n plus d choose n many monomials to choose from. But the vector space of evaluations at all points in K with components indexed by the derivatives will have dimension n plus n minus 1 choose n times size of K. Right. So let me start with this assumption. Suppose n plus n minus 1 n choose n times size of K is strictly less than n plus d choose n. What this really means is now there is a non-zero polynomial in the larger sense of derivatives. So there is a polynomial in the span of 0 to q minus 1 to the n sum m sub m, which is non-zero, such that the degree is at most d, and the polynomial vanishes for all derivatives with order at most m minus 1 at every point of the Kakeya set. So it's not simple vanishing at every point, it's vanishing with order at most, vanishing with order m at every point. All derivatives of order at most m minus 1 must vanish, not just the polynomial. All right. How does this help us? So once again, the rest of the proof is fairly similar. You divide the polynomial into its homogeneous components, restrict it to a line, blah, blah, blah. So I'm skipping those similar arguments. You'll get a contradiction. You'll be able to conclude that the polynomial is in fact the zero polynomial, contradicting the initial assumption. Therefore, the size of this Kakeya set must be at least this ratio, n plus d choose n by n plus n minus 1 choose n. Let's go back. What was m and d? Well, m was a large number. It was 2l minus n by q. D was lq minus 1. And L is a free parameter for us. Doesn't matter what L you choose, this bound will hold for the appropriate m and d. So let's now take L tending to infinity. And then estimates on the binomial coefficients will give us a lower bound of q to the n by 2 minus 1 by q to the n, which is roughly q to the n by 2 to the n. So this is further lower bounded by q to the n by 2 to the n. And that completes the proof. So the gist is that extensions to multiplicities, whenever possible, can never give you a worse answer. They either give you the same answer or they'll give you a better answer. Right? So in this case, we get a better one. And another point to note is we are essentially considering not one instance of a multiplicity parameter. We have to take multiplicities tending to infinity. That's where the gain comes from. Okay. So really, really large multiplicities tend to give us better answers. So that's the one short lesson to learn from it. All right. So yeah, that's where we are. Let me move on to another problem. So this completes my intended discussion on extensions to multiplicities in the sense of derivatives, etc. I'll move on to a different problem and a different application of the polynomial method. So are there questions up to this point? All right, so let's go ahead. A very similar problem, the finite-field Nikodym problem, but with a very different answer and a very different approach. All right, so you are not to be blamed if you think that this definition is very similar to what you just saw earlier. So a set n in fq to the n is said to be a Nikodym set if for every point in the vector space, there is a direction d such that the line along that direction passing through the point is contained in the set. Okay. I have made a small error. It's almost contained in the set. So it's not contained in n. I could exclude a. So the line is contained in n minus a. Okay, so that's a small mistake. Sorry. So LAB is contained in n minus a. What's the difference? Well, this is some sort of a dual definition. In the Kakeya set case, for every direction, there is a line along the direction that's completely contained in the set. Here, for every point, there is a line passing through the point that is almost completely contained in the set. That's the difference. Although the definitions are very similar, these are not quite related to each other. The relation between them as far is to the extent of similar questions being relevant and similar proof techniques being relevant. That's it. But formally, there's no connection between these two objects. Okay, so once again, extreme question. What is the least size of a Nikodym set? Again, by the definition, it should be the intuition should come to us that such sets cannot be very small. Okay, so what's the least possible size? In 2008, Lee gave a very similar proof using polynomial method, saying that the size of any Nikodym set is in fact at least n plus q minus 2 choose n, which again by binomial estimates will give us q to the n by n factorial. And here we consider polynomials with degree at most q minus 2. That's the proof. So I'm not repeating the argument here. It's very, very similar to the Kakeya case. In fact, it's much simpler. In this case, you do not need to consider homogeneous components of the polynomial. You might as well work with the polynomial right away. Okay. So we have this lower bound, very, very nice lower bound by Lie via the polynomial method. However, all known constructions of Nikodym sets have much larger size. So this in the Kakeya setting, q to the n by 2 to the n is known to be nearly tight. So there are constructions which achieve this bound up to a factor of 2. So very close to being tight. However, there is no Nikodym set construction which is known to be of size close to q to the n by n factorial. In fact, all known constructions have size almost as much as q to the n. So if you fix the dimension n and take q tending to infinity, then we only know constructions which have size 1 minus little o 1 q to the n. That brings us to this conjecture. Is this lower bound in fact much stronger? So the conjecture is that for fixed n and q tending to infinity, every Nikodym set will have size at least 1 minus little o 1 times q to the n. And this conjecture is in fact open even now. There's a partial result that comes from a very different application of the polynomial method, which is what I would like to show you now. Okay. So what I would like to talk about is a formal object called the lift of a linear code. But instead of getting into the abstract definitions of what these are, I'll restrict my attention to subspaces given by polynomial evaluations. So linear code, and the terminology just comes from coding theory. What we are really concerned with is codes given by polynomial evaluations, which are simply evaluation vectors of polynomials. Okay. Right. So for any polynomial in this span, that's basically any function on the vector space of q to the n, with degree p at most d, and any line in this vector space. Right? Every line in the vector space is of the form can be parameterized as a plus pb for some fixed a and b. Right? So for any polynomial with degree at most d and any line, it's obvious that when you restrict the polynomial to the line, you get a univariate polynomial whose degree is also at most d. Right? Obvious statement. This is what we have been using so far. The question is, how far can we improve on this intuition? Surprisingly, there are other polynomials with much higher degree, which when restricted to lines can have lower degree. So if you simply put the condition, if you do not require that the polynomial has degree at most d, instead if you simply say restrictions to lines must have degree at most d, you could in fact work with polynomials of much higher degree. So how does that work? So to quickly give you an example, let's say q is a large power of 2, and consider the monomial x to the q by 2 times y to the q by 2, two variables. And if I restrict this to any of the lines y equal to cx, where c is non-zero, the resulting polynomial has degree 1, but the original polynomial had degree q. Right? So yeah, this is the simplest example of the degree falling significantly when restricted to a line. Although the degree need not fall as much. Here the fall is from q to 1. It could be anywhere in between. But the idea is degrees can fall significantly when restricted to lines. How far can we exploit this idea? So once again, back to the statement, back to the question, what's the least size of a Nikodym set? GOCC and Subin in 2030 proved the conjecture by exploiting this idea in a partial setting, in a restricted setting. So what's the restriction? Q cannot be arbitrary. I'll have to first fix a prime P and then only consider powers of P. Okay, so as a combinatorial statement, a lower bound on the Nikodym set is expected to be just a function of Q and not really depend on P. So the dependency on P is the restriction in the result. You will have to fix P and then only consider powers of Q, only consider powers of P. In that case, this conjecture is true. So how does that work? So now I am considering a slight variation of the kind of polynomial vector spaces that we have been looking at. I consider VQ minus 2, which is defined to be the space of all polynomial functions. That there is no degree restriction on the polynomial itself. The space of all polynomial functions, the only restriction is, of course, the one coming from the Nullstellensatz. So the space of all polynomial functions such that when restricted to any line, the degree is at most q minus 2. Obviously, every polynomial with total degree at most q minus 2 is here, but there are many more. That's the idea. And that's what we would like to explore. That gives us a sharper bond. Okay. So the proof is again very, very similar, but we work with this vector space, which has a larger dimension. How large? Well, we can show that there is an epsilon which is dependent on p, and that's where the restriction comes. Epsilon dependent on p between 0 and 1, so the dimension is as large as q to the n minus q to the 1 minus epsilon times n. And this epsilon is inverse in p. Let me just stop by saying that it's a complicated expression which is further lower bounded by q to the n minus q to the 1 minus epsilon times. So, but the proof is, rather the computation is fairly intuitive. We are not really counting dimensions in any haphazard way. We are only counting larger degree monomials, which when restricted to lines are of degree at most q minus 2. That's all that we're doing. So the dimension of this vector space is at least q to the n minus q to the 1 minus epsilon times n. And therefore, by replicating the rest of the proof as it is, we can conclude that the size of the Nikodym set is at least this much. So when p is fixed, epsilon is fixed between 0 and 1, and this is exactly 1 minus little over 1 times q to the n, when q tends to infinity as a power of p. Right? When you vary p, for instance, if you take q equal to p and then take p tending to infinity, this bound becomes 0. That's why you really cannot exploit this any further. Okay. Right. So that's the idea of a lift. So why did I call it lift? So there is a more general theory of lifts for affine invariant linear codes. In fact, any subspace given by polynomial evaluations is affine invariant. And lifts are essentially defined in the same way. So these are all code words. When restricted to lines, they'll give you code words of much smaller degree or much smaller complexity. That's the idea of a lift. Okay, so this was the other different interpretation of polynomial method, which actually works to give you a nice answer in the case of the Nikodym set. All right, so yeah, I think this is where we stop this discussion. So once again, if there are questions, I'll be happy to take. I just have one more short problem to talk about.
Can we use this approach for the that you have shown for the Nikodym problem also for the first problem you have shown us to get better bounds?
It would work. So that's a good question. So what happens is the following. In the case of Nikodym set, we are only concerned with vanishing of the polynomial. But in the case of the Kakeya set, there are two kinds of vanishing that we need to consider. There's the vanishing of the polynomial as well as the vanishing of the highest homogeneous part. And it turns out that when you consider this kind of an approach, you really cannot say anything more about the vanishing of the highest homogeneous part. So yeah, the bound cannot be improved. And in fact, it really should not work because this is too strong a bound to work for the Kakeya set.
Thank you.
So yeah, in a sense, you're right. So there is a lot of takeaway in the sense of intuition. So when you work with one problem, let's say apply polynomial method to the Kakeya set problem, one might as well borrow a lot of intuition and then try to apply similar ideas to the Nikodym set problem. So there is a lot of flow of ideas and intuition, but formal proofs may not really carry on from one place to the other because of very, very subtle differences. So the subtle difference in the Kakeya set case is that we need to understand the vanishing of the homogeneous part as well, the highest homogeneous part as well. Okay, so let's move on to the third problem that I want to talk about. This is a much shorter exposition because the proof in the third case is really, really long. So I'm just going to make it very short and just give you a glimpse of what it is. Okay, so this is what's called a capset problem, and some of you might have been familiar with this. It was solved fairly recently, just a few years ago. So we are concerned with arithmetic progressions in the finite field, or in vector spaces over finite fields. So what's a three-term arithmetic progression? It's a set A, B, C, a set of three terms, such that there is a common difference between the two. So C minus B is equal to B minus A. Right. And of course, we had to consider A not equal to B not equal to C. Right. So this is a set of three elements such that, in other words, this equation A minus 2B plus C equal to 0. This is satisfied. Okay. Why are we interested in three-term APs? Because this is the first case of a non-degenerate AP that you could consider in vector spaces. Right. Okay. So a set of points in the vector space is said to be a capset if it has no three-term arithmetic progression. And to give you some idea of what's really the intuition behind the name capset, so if you take two terms, A and B, and then try to follow it up with the next term, C, if the set does not admit a three-term progression, then the term C cannot progress in the same direction. It has to fall to some other direction. So it should probably look like a cap. That's the idea. Okay. So a capset informally is a set of points where every set of three distinct elements forms a cap. It can never be an arithmetic progression. Okay. And now some intuition should indicate that if you have lots and lots and lots of points in the set, let's say points that are nearly as much as q to the n in size, then one will not be able to avoid the presence of three-term arithmetic progressions. Right? If there are too many points, then APs will pop up. And that, which is why we restrict ourselves to three-term AP, just the smallest case of AP that one could think about. So if there are too many points, then arithmetic progressions with three terms should pop up. So the extremal question in this case is, how large can be a set of points which does not admit any arithmetic progression or any three-term arithmetic progression? So the question is, how large can a capset in FQ to the NB? Right. Once again, this is a proof by the polynomial method, but via a third kind of application, not really looking at evaluations or roots or multiplicities in the conventional sense. Okay, so this is once again a product of two independent works. Groot, Levin, Park sort of invented this approach, and then Ellenberg and Geisweit refined this approach further. So the result says, for any fixed q, there is some real number theta less than q, such that as the dimension goes to infinity, every capset can have size little o theta to the n. Okay, or more weakly, little o q to the n. In fact, it is far away from q to the n. Okay. So a capset cannot have size anywhere close to q to the n. It has to be significantly smaller than q to the n. That's the answer. This was a conjecture for a long time, and Groot, Levin, Park came up with this idea of constructing matrices via polynomials and then looking at the rank, and Ellenberg and Geisweit sort of refined their approach. So what is this method? Okay, so a more general statement given by them is the following. Take any three elements alpha, beta, gamma, where gamma is non-zero, such that they sum to 0. And let A be a finite set, such that the equation alpha A plus beta B plus gamma C has no non-trivial solution. Okay, the only solution for this has to be A equal to B equal to C. So if you take alpha equal to 1, beta equal to -2, gamma equal to 1, this is the capset. condition. Okay. So if A is any, let's say more generally, alpha, beta, gamma capset, then the size of A is at most this quantity, 3 times the number of multi-indices where every component is at most q minus 1, and the total degree is at most q minus 1 times n by 3. Okay. It's a fairly weird bound, but there is a lot of intuition that goes into this. So estimates on the right hand side will finally give us the answer that we were looking for. So, but the technical result is this. The size of the capset is at most this. This turns out to be little o theta to the n for a suitable theta less than q. All right. So let me just fix another notation since this is a weird quantity. Let me say m sub d denotes the set of all vectors with degree at most d. So the claim here is that every capset has size at most 3 times m q minus 1 n by 3. All right. So once again, a quick proof outline just to show you how this method is different from the rest. So all the parameters are as given. D is fixed to be 2 times q minus 1 times n by 3. Alpha, beta, gamma are as given. And we have a capset A. Okay, an alpha, beta, gamma capset. Okay. So let me take a polynomial which is non-zero in the span of the monomials with degree at most d, where d is fixed to be this, such that p of alpha a plus beta b is equal to 0 for every pair a comma b which is distinct. Such polynomials will always exist once again by the linear system condition. You can formulate a suitable linear system with less constraints than variables and get a non-trivial solution. So such polynomials exist and the degree can be at most 2 times q minus 1 times n by 3. But this is a weird condition, alpha a plus beta b. These are the evaluation points that we're looking at. So what we really do is now construct a matrix after this polynomial. So let's say dp is a matrix of size mod a cross mod a, where the a comma bth entry is just the evaluation of p at alpha a plus beta b. Okay. And now what you really do is not really look at the roots of the polynomial. Instead, look at the expression of this polynomial as a sum of monomials. It has a unique expression type. Look at the expression, but now in 2 indeterminates. Since the evaluations are alpha a plus beta b, these are the evaluation points, one might as well consider the formal polynomial p of alpha x plus beta y for 2 sets of indeterminates x and y. Now write them down as a sum of monomials. This polynomial has degree at most d, which means for every monomial here, the degree in the x variables and the degree in the y variables must both be, at least one of them must be at most d by 2. So the degree in x variables and the degree in y variables, if both are greater than d by 2, then the total degree can be greater than d, which is not true. So at least in one set of coordinates, the degree is at most d by 2. And you can use a simple degree condition and decompose the matrix dp as a sum of at most 2 times md by 2 many matrices, each of which has rank 1. A very simple decomposition into a sum of rank 1 matrices. And therefore, the rank of this is just at most 2 times md by 2. Following this is a fairly simple computation of looking at the complement of A and using the capset property to lower bound the rank. Okay, and then you can put these two together and then get the final answer. But the main crux of this proof is to look at this matrix constructed out of polynomial evaluations. So two differences in this. This is very much a polynomial method because you're looking at a vector space of polynomials bounded by degree condition. But we are not looking at the roots of the polynomial or vanishing conditions. Well, vanishing conditions dictate the polynomial that we want to work with. The polynomial must vanish at all points of the form alpha a plus beta b, where a is not equal to b. But we are not using this to say something about the polynomial. Instead, we look at the matrix constructed out of this polynomial and the structure of the monomial expansion of the polynomial gives a structured decomposition for the matrix that arises out of it. A very simple decomposition into a sum of rank 1 matrices. And then the routine computations finally give you the final bound. Okay, so yeah, that is as much as I wanted to show you about this third variant of the polynomial method. So yeah, that's about it. And that's the formal end of this talk. So if there are any more questions, I can take them.
Let's all thank the speaker. I need to pull up my gallery view, but do we have any questions?
Yeah, I have a question. So if I have some combinatorial problem, do you have some recommendations when I should try to look for a proof using polynomial method? So what is the flavor of the problems where I can apply something?
Right. So one quick intuition is problems from additive combinatorials definitely have a lot of likelihood to admit a polynomial method kind of proof, because a lot of the times you can use whatever additive combinatorial restriction you have to put some sort of a structure on the vanishing set of the polynomial, and then you can look at roots or look at matrices or whatever it is, and then try to say something. But more importantly, what I would also say is that sometimes, or rather most of the times, a simple application of the polynomial method as we know it will really not work. These are very exotic examples where just a half-page proof just solves the problem by just one single shot application of the polynomial method. Often one has to adapt the method to the problem. So one should rather open ourselves to several variants. That's more or less the aim of this talk, to show that it's not just simple evaluations and roots that will count. In fact, simple evaluations and roots might not give you anything. But then one has to go ahead and look at other interpretations of evaluations. Well, for instance, in the capset problem, evaluations were used to construct a certain matrix, a very structured matrix, and you could say something about the rank. In the case of the Kakeya problem, we got a better bound by looking at vanishing conditions, but with higher multiplicities. In fact, multiplicity is going to infinity. So, right. So my intuition is linear algebraic problems, additive combinatorial problems can definitely admit a polynomial method kind of proof, but it will involve a heavy tailoring of the polynomial method to suit the problem. And that is really the work here. So the work is not really in understanding what the proof is like. The arguments are usually not very complicated, but the work essentially goes into cooking up a technique of working with a certain vector space with certain conditions, which will work for your problem. Once you have that, the proof might just be over in 10 minutes.
Thank you.
For instance, yeah, I could remap this. So let me go back to the Nikodym problem statement. So this is the proof that we had. And the dependence here, this is a partial result because we have this dependence on the prime characteristic P. And there is really no way of avoiding this P, at least by this technique. So even if one wishes to employ the polynomial method, one has to move away from looking at restrictions of polynomials to lines and come up with some other interpretation of the polynomial method. A simple question that anybody could ask is, we have only looked at simple evaluations in the case of the Nikodym set. Why not consider multiplicities? Turns out that you could consider multiplicities and look at higher order vanishing, and it would still give you the same bound. The dependence on the prime characteristic is not going to go away. This bound is not going to improve either. So this is one nice example where even extension to multiplicities does not give you anything better. So it really calls for a different interpretation of polynomial method.
Yeah, thank you.
Yeah, sure. Something in the chat. Okay. Yeah. Thanks.
Are there any other questions for the speaker? Well, let's then thank him again.
Okay. So